So this is joint work with my student Vashish Tabadunla, who is graduating next year, my colleagues Vineet and Asaf. So let me say first what I'm talking about. So I'm considering assortment optimization problem. What it means is that you have to present an assortment of products to a customer, and the customer picks one of them. And the main point is that the probability of a customer to pick an item depends not just on the individual items, but the set of items that you present. So for example, if this is a set of headphones that Amazon is showing the customer on search of headphones, there is some probability of choosing each of these. Let's say customer is thinking this one looks good, but then if I add this new option, which is much cheaper, has much better reviews, then suddenly the probability of choosing the rest of them also changes. Or if I have a movie suggestion or TV show recommendation, I'm presenting an assortment of TV shows to choose from, and customer is thinking among which one to pick, and then I add this, things change. And so this problem of how to model customer choice behavior when you present an assortment is not an exact science. It has been studied in econometrics and marketing science for a long time. And what I'll do is start from a very basic model, which is the multinomial logic choice model. And already we run into problems when we try to learn this model. So what is this choice model? So here, simply we are saying that when you present an assortment S to the customer, then the probability of picking item I is renormalized based on what items you present. Okay, and so there are n parameters, one for each item, each possible item, and V0 is the parameter associated with no purchase option, right? So the customer might not take anything from your assortment. So one important property or constraint you can say of this model is that you are assuming independence of irrelevant alternatives. So the relative probability of two products doesn't change just because you added a third product. So for example, relative probability of these two shows doesn't change because you add these. They both may go down or go up, which is unlikely. Now, what is the assortment optimization problem? Now imagine that each item, in addition to having a probability of being clicked, there's also a revenue associated. For example, how much money you'll get if the customer buys that product. You have these rewards associated, and you have these parameters. And the assortment optimization problem, if you knew everything about the model, would just be to find the assortment that maximizes this total revenue. Now this is not the top K problem, because even if you are selecting a K set, it's not a top K because there is an interaction between reward and the choice probability, and the choice probability depends on the entire assortment that you present, even though in this simple way. Now for this problem, when you know the parameters, there are efficient LP solutions available. This was at one point an active area of research in revenue management, but kind of solved for the K cardinality problem. But what is the learning problem now? What's the bandit version of it? Now imagine that you don't know these parameters, right? The only thing you can do is you can offer an assortment and see what the customer picked. Okay? So you offer a K cardinality assortment to the customer, at most K, and you see the choice, and then whatever way you can update your estimates of these parameters, you can update them and go on. Okay, so over T rounds, now you want to offer these sets while learning the parameters, and you want to maximize the total revenue, where the revenue function is this thing with rewards times the choice probability. And as usual, we'll try to minimize regret, which is if I knew the whole model, I could compute the best assortment and offer it all the time compared to what I am doing. Okay? Now, I won't go into related work a lot. Basically, as I said, this for K equals 1, if you're offering a single product, this becomes a multi-arm bandit problem. So you're expecting a root NT type of bound at least, or at most, I don't know. And we can show actually a lower bound. We can show that you cannot get better than root NT over K. We believe the lower bound is not tight. It should be root NT. And in a previous paper, we did show an upper bound of root NT using UCB type of arguments. What we do in this paper is actually show a more efficient Thompson sampling based approach, which also gets root NT. Now let me summarize the Thompson sampling approach, which is a very natural heuristics for multi-arm bandit problem. The way you would do this for this problem is whatever parameters you're trying to estimate, the V0 to Vn, you would maintain a posterior distribution on them. Okay? So you'll start with some high entropy prior like uniform distribution. And every time you offer a set and you observe the choices, you'll do some updates to these posterior distributions. And I'll go into how to do that. And the idea is that every time you have these distributions, you sample parameters from the distribution, and then you pretend that these are the true parameters and pick the best assortment. Okay, that's the way the algorithm will keep going. Now, in my multi-arm bandit, this is the optimal algorithm. It has been shown. Now, what is the problem in doing this for MNL? The problem is that updating this posterior is really difficult. What you're getting now is a choice he made based on the entire set. So you have like a joint distribution over parameters that you need to update. And so our question was, can we do it simply? Like you can simulate in some Gibbs sampling and all that, but we didn't want to go into that, mainly because it was very hard to analyze that. So we wanted to do it simply, and we used three main ideas to do it much simpler and so that we can analyze it. One is that we say, okay, since we have independence of irrelevant alternative property, we have that ratio remains fixed. Can we estimate these ratios, marginal distributions over these ratios? So what we do, the main trick is that we actually take an assortment and offer it again and again until we see the no purchase. And then we can show that the number of times a particular item is picked in this epoch is actually an unbiased estimate of this ratio between Vi and V0. Okay, so that gives you an unbiased estimate of marginal parameters. Using this, we can maintain marginal posterior distributions for every one of these ratios. We have lost the correlations between them, so that's a big issue. And let's say for now we take independent distributions over each marginals. This is like a very toy simulation showing that you still get much better performance than UCB. So red is UCB and green is Thompson sampling. We could still not analyze it, which kind of made us think that maybe we should not do it this way, we should introduce some correlations. And the next step we did to introduce those correlations was to actually first approximate the posterior. We want an even simpler posterior, so we did the obvious thing, let's approximate by Gaussian. So we take the posterior mean, take the posterior variance, approximate by Gaussian, makes things a little worse. So this pink thing is what we get then. It's fine, it's a little bit setback. The third and final thing we do is we now correlate the samples. So what we do is, instead of generating one independent sample from every Gaussian posterior, we generate one standard Gaussian and generate the samples as transformations of those. So they are all positively correlated samples. Not only did this make our life much simpler in analysis, and I don't have time to go into analysis, this actually improves the performance. So it means that we were losing some correlations over there. I don't know, is this the best way to introduce correlations? But in the analysis, it seemed like a good way. And we actually see benefit in empirically also. And we did one minor change, which is we also take more than one sample from this standard Gaussian, K8 samples. And all these ideas was inspired by the theoretical analysis, but we saw that this actually makes sense to also do empirically. So there is an open question in some sense that in such a cases where you see these effects of joint effects of your parameters, what's the best way to use posteriors? So the overall result, the theoretical guarantee we get is that you can get square root NT log T under a mild assumption that the no purchase option has the highest probability among all the options. And we have a lower bound for this case, which is square root NT over K from our earlier paper. Future directions include closing the gap between upper and lower bound. We strongly believe that the upper bound is right, but we don't have a proof to improve the lower bound. And there is a general, as you said, we only have scratched the surface of this problem. This is the simplest model you can think of in customer choice behavior. There are a lot of other models which don't have IIA property. There's feature-based learning questions and so on. Thank you.
Thank you. So we have time for questions.
Yeah.
Claudio?
The curiosity I have is this process you showed are generated by synthetic experiments?
Yeah. So this was supposed to be a theory paper. Like the plots were really like toy experiments. This is like 1,000 arms simulated using some randomly generated parameters. K equals 10. But we have been doing some experiments recently to see.
Way of correlating these estimators helping you in the theoretical analysis.
Yeah, it was inspired by our theoretical analysis, but it was a bit of surprise for us that actually it improves the experiments, and then when we thought about it, it seemed logical that it improves the experiment. Yeah.
Okay, thank you.